So to just make us like a few notes on Unit 5. This I don't even know if we need to write it down because I'm pretty sure you guys all have this pretty well memorized. But Unit 5 is primarily like your increasing, decreasing, maximums, minimums, concavity, those sort of things. So one of the key things you got to know from Unit 5 is that chart, which I think you guys know pretty well. If f is increasing, then f prime is positive. If f is decreasing, f prime is negative. If f is concave up, second derivative is positive, which means that f prime is increasing. And we got concave down, we got decreasing and negative there. So this certainly is in that section. I think a lot of you still draw this chart or parts of this chart next to your problem. So I think we're pretty good with that. But it's kind of the basis for everything that's in this unit. One thing that's important to know from this section is the difference between a relative maximum or minimum and an absolute maximum or minimum. So if you see absolute max or min in the question, if they ask you to find the absolute maximum or minimum, you would need to set f prime of x equal to 0. Sometimes you're finding this from a graph, sometimes you're finding it from an equation, but it's the places where your derivative equals 0, what are they called? To find critical points. And then test the endpoints and the critical points by plugging them into F to find the highest or the lowest value. Sometimes you can rule out a critical point. Like if a critical point is going to be a relative minimum and it's asking you for absolute maximum, you can kind of throw it out. You don't have to test it, but it doesn't hurt to test it there. So you are going to have to like plug in numbers to the original and find this. This could be presented in a lot of different ways, right? So that is for absolute maximum or minimum. There are two different ways that we can find a relative maximum or minimum. So relative maximum or minimum, right? We either can use the first derivative test or the second derivative test. We usually used the first derivative test when we're doing these problems, although there are some where you have to use second derivative test. For the first derivative test, if you have a relative maximum or relative minimum, what happens with that first derivative? It changes signs. So for a relative maximum, f prime of x switches from what to what? Positive to negative. And if it is a relative minimum, f prime switches from negative to positive. Okay, that's your first derivative test. That's the one we use most often, but there's sometimes it won't work, and you have to use the second derivative test. The biggest times that it will not work, this is going to happen if you have like an implicit differentiation. Problem, so like that number 6 that we just looked at, the derivative has x's and y's, so you can't make like a sign line for it because you got x's and y's that have to be plugged in. So if you have implicit differentiation, which is like your dy dx equals x plus 2 over y, or something like that. I'm going to write that down too. Something like this. Yeah, something like that. You can't make a sign line. You can't tell where your derivative switches from positive to negative. Or f prime is not given. So they may only give you the second derivative and just give you like a little piece of information about f prime, but you don't have f prime's like actual value, except for maybe at one point. You have to have it at one point. So those are the times where you're going to have to use second derivative test. Now you can use the second derivative test on some of the questions that you can use the first derivative test on. So if you prefer it, you can use it. But we didn't really stress it much, so I doubt too many of you like prefer using that. For the first derivative test, the first thing you are going to do is f prime of x must equal 0 at that point. So most of the time in a second derivative test problem, you'll also know like they're asking you, is x equal to a maximum or minimum? They're not saying find it, they're saying like where, or is this point a maximum or a minimum? So your first derivative has to equal 0 at that point, so you are still finding like critical points. And then if f double prime of x is greater than 0, what does the second derivative being greater than 0 tell us about the function? Okay, then f is concave up, and f has a, if your graph is concave up, you have a maximum or a minimum point. Minimum has a relative minimum at that point. And then if f double prime of x is less than 0, so you got a negative second derivative, f is concave down, and f has a relative maximum at that point. Because if something is concave down, it's going to have a maximum point. Yeah. And if the second derivative equals 0, you got to use the first derivative test. So if the second derivative also equals 0, you were trying to do the wrong thing there. You need to go back and do first derivative test.
If that happens and your first derivative is also 0, would the answer to that be that it's not an actual limit?
It can still be, you can still have a relative maximum or minimum at that point. What's happened probably, this doesn't happen in a lot of types of functions, but like if we had some sort of like piecewise function where we might have a second derivative that maybe doesn't, like, well, hold on. It wouldn't exist if you had a sharp turn. It's not a guarantee though. I can't remember the condition where you still need to test like whether or not your first derivative switches from negative to positive. I think what happens, it's like if you have, I should still, second derivative equals 0, it is usually a change in concavity. I guess it's not a change in concavity if the second derivative does not change signs. I don't think you're going to run into it though. I think that we're probably spending too much time talking about that. All right, let's see. This section also includes mean value theorem. So, mean value theorem. Mean value theorem, if we think of it as a graph, we got some sort of function, we'll call it f of x, and then we got like a point A and a point B, so like right here and right here. So what are your conditions for the mean value theorem? Continuous, so f must be continuous. Technically, it's continuous on the closed interval from A to B and differentiable from on the open interval from A to B. Just means you don't have to be differentiable at the endpoints. That rarely becomes an issue. Most of the time it's just going to be continuous and differentiable everywhere, so it's fine. So f must be continuous and differentiable. And then if that condition is met, then at least one point for A less than C less than B, f prime of C has to equal f of B minus f of A over B minus A. And what that means, this part right here, that is your slope between endpoints. So if I draw it over here, it's the slope of that line between those endpoints. And f prime, what does f prime give you? What does it represent on a graph? Slope of the tangent line so there's got to be one point somewhere on this one. I think it's probably about right here where your tangent line and your slope between the endpoints are the same. So like in this case, C would be right here for that. So a lot of times here, you'll get something like you've got this function on this interval. Prove that the derivative has to equal 7 somewhere, right? And so it's usually that slope between the endpoints. How do you know it's mean value theorem and not intermediate value theorem? We're talking about derivatives, right? So intermediate value theorem only deals with the function itself. You don't talk, really intermediate value theorem doesn't have to be a calculus idea, right? You could technically teach it earlier because it doesn't deal with derivatives or integrals at all. It is just, if you go from here to here, you got to cross this line in between. So if you see something like this and it makes you think intermediate value theorem, but you're seeing f prime equals something, then that is mean value theorem for that. All right, let me look through here.
You don't have to say that it's differentiable.
You do not.
If you did, like, would they come out for it?
Most of the time in those cases, like especially if it's on free response, on multiple choice, it's not gonna matter really. But it's on free response. Most of the time in those cases, they've told you, like in the stem of the problem, that the function is differentiable or twice differentiable or something like that. So most of the time, what you have to say for intermediate value theorem is since f is differentiable, f is also continuous for that. So that is what you usually see, unless it's just stated to you that it's already continuous for that. So you're kind of mentioned differentiability with your continuity, but you don't need it there. All right, let's see. All right, I think that's all I need to review with you about about Unit 5. All right, so